Okay, welcome everyone to this daily colloquium on 20th of October, right? 2022.
Yes.
And I'm very happy to welcome Professor Dr. Christian Rothenberg from University of Campinas, Brazil. Christian is an associate professor there and the head of the Information and Networking Technologies Research and Innovation Group. He also received a PhD in 2010 in electrical and computer engineering, and before that he holds also a telecommunication engineering degree from Technical University of Madrid and also a diploma engineer degree in electrical engineering and information technology from TU Darmstadt, Germany. And he contributed to many patents, co-authored 3 books, over 200 scientific publications, including top-tier scientific journals and networking conferences such as SIGCOMM and Infocom. And we're very happy to have him here in this setup to give us a talk about the role of machine learning in fluid network control and data plan. I think the idea is that, Christian, you give the presentation now, and after that, we have some time for Q&A. Thank you very much for taking your time and joining us here. And the presentation floor is yours.
Thanks, Christian. Thank you, everyone, for attending this talk. It's my pleasure to share with you some of the updates on the field. It's a networking-centric talk, but of course, there are the machine learning bits and bytes. And I have structured the talk in the following way. So I will talk about this concept that I coined, these fluid network planes. I presented it a few years ago, and it keeps evolving. It's a way of explaining what is going on in the networking domain through network softwarization, hardware programmability, edge, and so forth. It's just a way of framing it. There are multiple examples, instances, towards its realization and its operation, the machine learning plays a key role. So I will comment a little bit about the opportunities and the examples of how machine learning is being applied in this context. And then I've reserved, considering, Christian, that your group also works a lot with video and Dash, adaptive video. Some of the really ongoing work right now is happening, these experiments with machine learning and YouTube, real YouTube over real 5G networks. And this is an ongoing work that we look for collaborators, we look to open the data set. So that's how I structured the talk. Just confirm with me, Christian, do we have how much time for this public presentation, like 40 minutes?
That's fine, 30? That should be fine, yeah, 30, 40 minutes would be perfect. Thank you.
Minutes plus 10 Q&A, or 40 plus 5 or something like that?
Yes.
Okay, then that's, there's a lot of content, so I will probably skip some of the details, and then we can always zoom in as per interest. Okay, this is a slide I usually use to introduce the audience. So what is behind this network softwarization, NFV, network function virtualization, software-defined networking, or intent-based networking? It's about the evolving networking landscape, moving from manual command line interfaces, closed source, vendor-led plans and hardware appliances implementing the specific functions like a firewall, like a load balancer, towards this new softwarized environment where the APIs, the modularization are key, automation, so getting humans out of the loop, having software automating control and management operations, a lot of open source at the software and even hardware level. The customers getting together to shape their roadmaps to through these foundations where they drive what they want from their vendors. And then the softwarization, so the hardware functions become modular virtual appliances. And this is the four key characteristics that I like to summarize independently of acronyms or so forth. This is another background slide that we need, because I will refer to these models of networks and basically to point to control plane functions and data plane functions. Both are getting programmable, and there are different models to realize this network softwarization. That's a topic for my grad class and other classes that I teach. But what is key here is to understand that a networking device has a set of functions that we call them control plane. So they calculate routes, they compute graphs, they exchange messages, like as a distributed database, to create state that is inserted into the data plane, into the memories, typically into hardware-based pipelines, which are the ones that take the decisions on the packet level on what to do with the packet, which packet header should be modified, what is the next hop, and so forth. And the interesting aspects that are happening over there is that these data planes are becoming increasingly programmable. These are these white box bare metal models that I'm showing here at the bottom. And what I will present about the fluidity is that these control planes and the data planes are moving throughout the network and also throughout the hardware and software embodiments. Okay. I'm not going to go in detail over this, but this is the last introductory background slide that I use to discuss research projects or papers to see where they fall into which aspect of the softwarization. Okay. Okay, so there are multiple SDN models, plugins, controllers, applications, the operating systems that run in the devices, how they are getting virtualized, all the software that needs to be in place to orchestrate both the virtualization of the infrastructure as well as the placement of the actual functions. And finally, how this data plane, in the example of the P4 programmability, it's getting out, it's less of a black box, but more of a gray or box where a high-level domain-specific language like P4 allows both researchers and developers of real products to define what the packet, the life of the packet it enters an interface, how the headers, the fields are parsed, understood, and what to do with these values throughout a set of stages throughout the pipeline. And then the APIs to insert tables, so state into this pipeline is getting also auto-generated and exposed to a control plane that could be local, close by, running in the same box, or remote in the case of controller-based SDN architectures. Good. That was all. I promise just a few slides to set the stage. I suspect not all of our audience today and later our networking audience or networking focused. I needed this to introduce what I'm calling this fluid networking landscape that we are facing. And as I already anticipated, in the current set of technologies, we have opportunities to implement functions both in the control plane and the data plane using a rich and unprecedented series of software and hardware technologies. Okay, that's the y-axis. And those functions throughout an infrastructure that accepts the instantiation of these embodiments allows also to place them into different locations, from the customer premises until the cloud centralized data centers. And then there is the edge, the famous edge that has different also sub instances. We have even the base station with a compute device as an edge. We have the multi-access edge computing framework by HC that recognizes multiple locations throughout the edge aggregation, access aggregation network where compute facilities can be put in place to host the applications and also the networking functions. Okay, and then we have the clouds in the access network and the point of presence data centers. Okay. So where to put which function and in which form factor? This is the fluidity that I refer to. If we look at the horizontal and the vertical, sorry, y-axis, we know that's a classical problem, whether you want more flexibility or and less performance, or you want a more inflexible, however, more performant implementation in the embedded system. And there are trade-offs from the architectural perspective that cannot be broken. So you cannot have, ideally you wish to have something fast and flexible, programmable, and also portable over different architectures. And this is unfortunately not possible. And in the networking domain, this is a classical problem that through some of the advances in the server technologies, in the programmable frameworks, are allowing for new sweet spots or design spaces. Okay, the difference is getting less and less depending on how you count the metrics. Here are some examples of the enabling technologies from the softwarization perspective, from lightweight virtualization, drivers to circumvent the kernel, or SDKs to like DPPK to accelerate the user, so the functions that the user plane in a traditional processor architecture. And then we have hardware accelerated features, FPGAs, GPUs, tensor processing units. All of these become a set of opportunities to run code. Eventually networking centric code, but also more application level type of code. Okay. We have programmability plus portability higher. The higher we go into this stack, into the software stack, and more performance as we go closer to the hardware. However, as I already said, advances in domain-specific architectures for networking, like this programmable language, P4, and the independent switch architecture, allows new unprecedented ways of programming networking functions, and not only networking functions, as I will show some examples. Here are some pointers. You will see these boxes throughout the presentation. These are recommended readings for those interested in the topic. So now looking at the horizontal, we now the big question here is to reduce latency. We know we cannot beat the laws of physics, and therefore we need to put the functions closer to where they are consumed. Closest to the client would be at their premises, at their edge devices, at their location, but inside the network, starting from a base station or an aggregation network, there are multiple options to place the applications and the networking functions. This is what is represented here. Also in this figure, we can see how to optimize these different locations that allow for some computing workloads to be instantiated, where to put this functionality is one of the opportunities that is being explored on through this fluidity of the network. And again, the trade-offs that we see here are latency and capacity, compute capacity plus cost, because of the reduced footprint that you have closer to the edge, compared to some cloud scale data centers where the cost of space, physical space, and the compute capacity is much higher. Okay. So now that we are virtualizing the functions and we have this portable functionality, we are decoupling effectively of where to run these functions. At the end, if you want the traffic to pass through a function like a firewall, what you want is that the firewall function is being executed at the right stage, but you don't bother where it's actually being executed. Okay, that's at the heart of NFV type of infrastructures. So putting together both axes, we can see something like this, where we can optimize for performance and cost, or for latency throughout these multiple opportunities. And from here, we can, I hope it becomes clear that multiple challenges from the design and operation perspective appear. So if you are the operator or the application designer or even the vendor, you have multiple choices of where to offer a solution. And probably the solution is not the best for, no, probably not, certainly the solution is not the best for all type of services. So you will want to have the solution tailored to a specific service. That's also how the concept of slices of the network is commonly referred to. Okay, so take your poison, choose something, but be aware what you are buying in terms of trade-offs. Okay, and you can choose to centralize more of the control plane functions in some data centers for the control part, and these have the data plane more distributed, and opt for more hardware acceleration at specific points, like at the edge, or be more softwarized at the at a point of presence where you will need more flexibility over time, and this is I guess one of the core design decisions that are taking many operators and many implementers have been taking into account. Of course, you need to orchestrate this for per service, so you need to orchestration refers to all the automated configuration, the deployment, the lifecycle management of the service, of the resource. Okay. And here is where machine learning also is often called for, to assist on the decisions of where to place, what to place, when to place, and take these decisions. That's where I will comment a little bit more throughout the talk. So let me show you some of the instances. Okay, just I will point here to multiple papers or works. I like to start with my own work. I will from time to time point to, of course, to a work that we have done. And this is an old one. This was route flow over 10 years ago, where we took Linux in Linux namespaces technology to run open source routing stacks over commodity hardware, and use this at the time new interface for hardware switches, which was called it's OpenFlow, to implement a router and we could implement the routing instances in a centralized server, so running BGP or SPF or the routing protocols, and having them mapped to physical ports in the actual network. And this was a lot of fun, including over a 9-month deployment at a live internet exchange point where we had to fake that we were a specific vendor box and using their MAC addresses so that no one would notice that that this split architecture was being in place and running effectively as the replaced box. Okay. And now we are seeing a lot of these examples where the virtual network functions are using technologies like DPDK or SmartNICs to implement accelerate the data plane. It was not possible to run in the user plane all the packet processing and therefore offloading them to hardware like SmartNICs, ASICs, FPGAs, or bypassing the kernel overhead are the key aspects, the key examples of how this software hardware continuing is being played out. Okay. Another example here, so you take part of the VNF and you offload the data plane to the FPGA running in a SmartNIC while you leave the control plane application running in the x86 server, for instance. Okay, another example with different types of VNFs in sharing the same server with multiple SmartNICs. And then we have recently seen the emergence of ASICs, application-specific integrated circuits, with programmable pipelines. Here are the example here are the Tofino line from now Intel that allow these new degrees of programmability at the same cost of chip size and energy consumption. You have a programmable device, so you have the opportunity to change the pipeline, and this is of course a game changer. Not for everyone, because you at the end you need to program it. It's a programmable target, so you need to know the domain, and you need, but certainly orders of magnitude easier than lower level programmability or platform technology specific programmability. This is an example at the Open Networking Foundation, where they are replacing the core functions of a mobile network, 4G or even 5G, and implementing the pipelines in this technology. This is something that we were also doing at the same time in collaboration with Ericsson. And this type of slicing architectures or slice capable architectures was something that we also explored in a EU Brazil project called NECOS, with multiple flavors on how to slice a cloud network architecture. There is also another related trend called in-network computing, or even at the IRTF with a specific research group, which is called computation in the network. And then there is this paper that summarizes very well what the main aspect is to have the network act as a computer, so to take the role of computation that usually was placed at the end host and take it over. And this allows to put to get any of the network device to act as part of the computation of a specific application domain. and getting towards the closest latency, and even at the hardware level, to the end clients. Okay, that's the main idea. And here we have a number of examples. There are works that are used in industrial type of applications, where the network devices, the switches that receive the packets from the end application, store information that allows them to make computation and take decisions as if there were the other part of the application there from a client server perspective. So the client remains the same, and some of the server logic gets offloaded and placed into a networking device. In this example, the colleagues, these are in Karlstad in Sweden, were implementing this type of fast react application. So they were parsing sensor data, like temperature data, and have the logic inside the data plane of a programmable pipeline to notify whether an average temperature was over a certain threshold. Okay, this is another instance, another example. Other colleagues have done also the offloading of key value type of stores into the devices. So these devices, programmable devices, pipelines have very fast memory architectures and very highly parallelized. These switches, they process packets at terabits per second. So imagine how many memory operations happen at this networking device. Of course, not fully programmable, but programmable initially for a networking domain, but some of the networking domains, like querying a database or storing a key and a value, or searching for a field inside a large table and getting the value, are at the heart of a networking function. And these guys smartly implemented a net key value stored through this net cache protocol by adding specific fields after the transport layer with operations of getting, putting, and deleting data into this and database offloaded to the network. Okay, in fact, we have also examples of how to implement the famous consensus algorithm of Paxos throughout the networking infrastructure, through top of rack, aggregate, spine switches. Okay, very interesting also instance, and now hitting also the machine learning domain, how to do in-network aggregation as a step inside a machine learning pipeline inside the switches or of the network, and combining with the GPUs available at the end hosts. This is another very interesting example of fluidity, where you offload to the network specific functions. In this case, not just network or control and data plane functions, but even application level functions. A networking centric use example are these by these two pieces of work, where they offload or accelerate some of the traditional control plane functions, like detecting a neighbor that is not responding to routing protocol messages, or from parsing routing protocol messages, identifying that some destination, some link is not available, and taking a decision at the data plane by having this inspection of control plane messages. Very interesting also examples on how to offload functions to the hardware. Another offloading problem that is interesting is whenever you have a machine learning approach, and the models related to the machine learning were to do the inference. And in the robotic application space, there are some constraints what you can run inside the CPU of the robot, and what you can do at the edge of the network or at the cloud. And this is a nice piece of work that shows this robot offloading problem that curiously we also ended up addressing, not so much machine learning specific, but for interesting applications like industrial applications where you want to control a robotic arm and identify and offload the ability of the cloud-based or server-based controller logic of sending the stop message whenever a certain location is being parsed. And this is something that we also proved as a concept, that a P4 switch was able to parse, store the positions of the robotic arm. These types of applications, the robotic arm sends over TCP with very frequent messages the current positions, and all the logic is placed in some x86 application at the premises or in the cloud. And the P4 device was able of identifying these thresholds and generating a valid application level message within the same TCP session as if it were the actual controller, and thereby reducing considerably the latency of this stop message. That's something we also played out in collaboration with Ericsson. And we took the same idea, and we are taking actually the same idea. I see Fabrizio is in the call over here. He's the main author of his PhD thesis, goes into this space where we are researching whether we can accelerate some collision avoidance algorithms by running centralized, but not centralized in the cloud, but centralized in the data plane functions where all drones get connectivity from. Okay, and you can see the video, and also it was a piece of work that was awarded and leverages also P4 programmability. Okay, the title of this slide is wrong. It's not robotic arm control offloading. It's collision avoidance of drones offloading to the edge, programmable edges. Okay, let me go a little bit deeper now into the role of machine learning. We have seen machine learning applications being accelerated by programmable data planes. Machine learning for networking, if you have been acting in the field, and in any field, in any area, we know how machine learning is accelerating, hitting, shaking many of the areas by their powerful opportunities that I'm not going to detail. So here are 4 surveys that you can see a myriad of applications, of papers, publications that explore how machine learning is being used or could be used to improve networking throughout all the layers. What I'm going, okay, these are some tables where you can see the structure of the survey and different applications domains. So fault management, congestion control, routing, traffic prediction, traffic classifications, by framing them as problems that the machine learning pipelines can solve. I will discuss a little bit what are opportunities specific to this fluidity, and then I will move over to the what we are doing in the 5G and YouTube streaming specific field. Okay, so from any softwarized network, the life cycle starts at a design time where you need to decide which hardware to run which software functions, or which logic of your end-to-end network design. And at the same time, there are many optimization opportunities. From hardware parameters, confirmation, actually configuration aspects that machine learning can assist to the actual code that is being produced throughout these layers of compilers. The P4 language is another layer of compilation with an intermediate representation language as well. And machine learning is being used to optimize this at the same time to get most out of your compilation target. Okay. Then still at the same time, but prior to deployment, to getting online, so offline still, you have many problems that relate to the classical virtual network embedding. So you have a demand for a set of capacities to run a set of functions, and you need to decide where to place them. But now the opportunities with all the layers of programmability are of a complexity that are hard not just to parse for humans, but also for the machine learning models themselves. So there are aspects of the target where you want to compile the P4 code, where you can compile the P4 code. Once it compiles, you know it will run, but it doesn't compile over any target, depending on the logic of your pipeline. What to offload in terms of hardware, where to the classical placement of the VNF to meet some targets is itself subject to many machine learning algorithms, and not just one function, but the chain of functions, what is called the network service. And also to estimate, once I have this solution, to estimate whether the end-to-end performance is likely to be met. But that was in theory. You need to go live, then you have real workloads, then you have real concurrency over resources, and this is the online runtime operations. And there you want to verify that the estimated performance is being met, and even predict that throughout some changing behaviors or boundaries that you were considering before placement, before going online, that changed, that there is no risk that some of the quality of service of SLAs that were agreed are going to be violated. And also then, as part of the machine learning aspects that are being explored, are doing recommendations, like advising the operator, the human operator, or even taking purely machine-based decisions on scaling up or down, so adding more CPUs, more resources to specific functions, or scaling out or in. That means creating more instances over different targets for a specific function to meet the demand and deliver the expected performance. So doing these recommendations either for humans to take the final decision, or for the software to take them directly. And here, these arrows back shows also that the DevOps type of working are also in place. So development and operations are closer than ever. So developers want the data from the real operations, and machine learning is also being explored in this feedback loop, both offline and design time. Okay, here are some examples. I mean, already starting to compromise the time, so let me speed up. Examples of running neural networks on the network interface card, taking decisions around control planes. Here we have done some work as well over different domains. So closed loop automation and doing machine learning, using machine learning to estimate quality of experience of the service, to predict, to do root cause analysis. This is something that that we have been and we are still exploring. And now moving towards the video domain, we have been working with Dash Video and taking to the edge the collection of metrics, flow level metrics related to this type of service, and estimating, since there is no access to the actual player or server of the video in many cases, not in all cases, but in many operator-centric cases, but where the operator would like to know whether the delivered quality of experience meets some goals. So we have implemented frameworks, reproducible, like using Jupyter notebooks, where we collect the data, we build the model, and then later we do the inference and estimate the quality of experience. And at the heart of these problems, where we want to be realistic, is to use some scenario that is close to a real networking scenario. And either you do at scale and you go throughout to the wild, or before that, you use some traces. And we, for some amount of time, we were using cellular network traces by others from 4G and 5G networks, and reproduce them into the controlled emulated environment, and run all these experiments at scale. Okay, and from there we were able to compare 4G versus 5G for different Dash adaptive algorithms, even for transport protocols like TCP, QUIC, and different versions of all the protocol combinations, looking into how the resolutions were varying over time, and looking at the distributions of the quality of experience using standardized KPIs. That was nice. That was, but we felt that something was still missing to close the loop. And to close the loop, we went in the wild. We are going in the wild. I think I see Rasa. Rasa was over here, the PhD student. Yeah, Rasa is over here, running this work, where we wanted first to validate that the machine learning algorithms that were used in the controlled environment would apply to a real network, and to enrich our data set for emulated environments using the traces from real networks. So there is this 4G, 5G trace collection effort going on with YouTube streaming, real YouTube streaming, that we could not find anywhere with all the level of details that we wanted to run the type of research questions that we are looking into. These data sets will become available soon, very soon. The main questions, research questions, are to evaluate the quality of experience of YouTube over different mobile networks. And when you say, okay, 5G, if you look, there is no just a 5G, there is 5G with dynamic spectrum sharing, there is the non-standalone, there is a standalone. So these we suspect, we are confident, and it's well known that they don't deliver the same levels of performance in terms of latency and throughput. And we wanted to know how does YouTube actually perform over these types of 5G instances compared to 4G. And to answer these questions, you need to do a couple of steps, like collecting data traces and so forth. The second big research question, and at least that's how I summarize Rasa's work, and that's good, Rasa, because he's finalizing his PhD. That's the way I express it. The second one is, can we predict a future quality of experience KPI, like a stall or a shift in the resolution by just observing network level features, some features that are available from the operator, at the operator, or even at the mobile device. So radio parameter related, or even packet level, flow level. And then the big one that we are looking for actions. So what to do after we know that in 5 seconds the video will stall or the quality will degrade. I know that the colleagues from the video codec and adaptation are doing tremendous work, and we wondered whether there is something additional that by talking to the network level that can be done. Okay, this is the other question. So without going into further details, I know I'm compromising the time. Rasa has put this framework using the iframe API of YouTube, installing this application into Android 5G capable devices, completed a large collection of data sets in France, and we are reproducing, crowdsourcing it with our students locally in Campinas, where we still don't have the standalone flavor of 5G, and moving also to the city of Sao Paulo to run experiments and collect the data sets for different types of use cases, as you may expect. Hopefully that can be compared in a fair, accurate way. These are some of the statistics of the data sets and details about the obtained results that I will skip for the time. We will present them at the end of the year in Globecom in a demo, and also open source as much as possible from all the data sets that are being collected. With that, and consuming all the time, I'll pass back the word to Christian and to you, and on anyone who would like to comment. I'm happy to discuss today or later at any time. And if you want to visit us in Brazil, we have also openings at all the levels, including professor, postdocs, masters, and PhD, and always welcoming motivated fellows. Thank you.
Thank you very much, Christian, for this awesome talk and overview of this very exciting research area. And indeed, I'm looking very much forward to this data set that you mentioned towards the end of the talk, which is definitely something that we, and I think the entire streaming community, will find useful.